Alright, in this video, we're going to look at several more differential equations that just appear in different applications. One is the differential equation for a hanging wire. So here, differential equation for a hanging wire. Okay, so what do we mean by that? So suppose we just had a wire hanging between 2 points. So these points are fixed and the wire just hangs down from them, like that. And so the wire is not moving, it's in equilibrium position. And there's actually an equation which gives the shape of this wire, okay? And so we're looking for kind of like the shape of this curve, a function y of x, and it turns out it satisfies this differential equation. I'm not going to derive it, I'm just going to write it down. So it's d squared y dx squared, so the second derivative of y is equal to w over t1. So these are just constants depending on physical properties of the rope and so on. And then times the square root of 1 plus dy dx squared. Okay, so this is a second order equation because the highest derivative appearing is y double prime. And it's also nonlinear because we have the first derivative being squared and it's also under the square root. So this is a nonlinear second order equation, but it's actually not too difficult to solve because there's a little technique we can use for second order equations when the dependent variable y is missing. So there's only the second derivative there and the first derivative, okay? So we can actually solve it, but we'll do that later. Okay, another differential equation. You may have seen this before in a calculus class when studying exponential growth, but it's Newton's law of cooling. Okay, so if you have, say, like a cup of coffee in a room and the room has some ambient temperature, the cup of coffee, if it was hotter than the ambient temperature, it's going to cool down and eventually reach the ambient temperature. Okay, so Newton's law of cooling says that the change in the temperature is proportional to the difference between the temperature of the object and the temperature in the room. Okay, so the change in temperature is proportional to the difference between the ambient temperature or the room temperature ambient and temperature of object. The object that's cooling down. Okay, so that just means that the change in temperature, so if we let capital T of t, little t is time, this be the temperature, this Newton's law of cooling says that the change in temperature, that is the derivative of temperature with respect to time, is proportional to, that means it's equal to some constant, okay, proportional to the difference between the temperature of the object, capital T of t, minus the room temperature, which we're assuming here is constant. So we'll just say TA for ambient temperature. Okay, so here capital T is a function of little t, and this is the room temperature, it's a constant, and K is a constant too. So this is an example of a first order equation, and it's also linear. And first order linear equations are very easy to solve, and we're going to look at methods like that later. Okay, so there's another example of a differential equation. I'm just going to move some of this up. Okay, the next one we'll look at is the deflection of a cantilever beam. Okay, so here we have some beam. I think of just like a diving board. Okay, so there's the beam, and it could be deflected. So say you walked to the end of that diving board and jumped off it or something. So then the picture would look something like this. I don't know, there's a deflection there. It's not a very good drawing. But this distance here, we're going to call y of x. So basically, the amount by which the beam is deflected, and it's going to be deflected along other parts of that x-axis there. So for example, it could look something more like this. Right? And so we're calling that position there, or the deflection at any point y of x. Okay, so it turns out the differential equation for that, I'm not going to derive it, has this form. Some constant e times another constant I times the second derivative of y double prime over 1 plus y prime. This y prime is squared, and then this denominator is to the power of 3/2. And then this is equal to some function w of x, which is known. So this is a differential equation for y, and it's very difficult because you have the second derivative of this quotient here, and this is also another nonlinear equation, obviously. And if y prime is small, right, then the denominator here, we can ignore that y prime there. And so then this differential equation just becomes ei times y fourth derivative, because it's the second derivative here of y double prime, and this denominator is just 1 if y prime is really small, equals w of x. So here, this one up here is nonlinear. And then if we make an assumption, in certain cases this would be a good assumption, then this is a fourth order linear. And you'd want to solve this differential equation for w. Okay, so there's just another example of differential equations that can appear in a physical system. We're going to look at just a couple more. Now we're going to look at some population growth. So this one's very simple. Okay, so if we let P of t be the population of some population, could be people or humans, it's a reasonable assumption to assume that the rate at which the population changes, that's the derivative of P with respect to t, the rate at which the population changes is just proportional to the actual population. So we could say like equals RP. So here we're saying that the population growth, or the rate of growth, is proportional to the population at that time. So the rate of growth at some time is proportional to the population at that same time. So that just means that the derivative of P is equal to R times P. Okay, so this is a first order linear, and it's actually very easy to solve. Also, we haven't really talked much about initial conditions, but this could come with an initial condition, say the population at time 0 is equal to p naught. The solution to this differential equation is just saying that the derivative of p is equal, if that r wasn't there, it says the derivative of p is equal to itself. And you know from calculus that the exponential function has its derivative equal to itself. And if the r is there, the solution is just p of t equals p naught e to the rt. So it's really easy to see that the derivative of this is just r times p. Okay, so don't really worry about how we solve that right now. We're going to go over that in later. But this is just a simple model right here. This is the model for population growth. So here, the population would be growing exponentially, which can't go on forever because usually there's some kind of carrying capacity. So a more realistic model would be the following. Would be if you had a population growing maybe exponentially and then went up and then kind of leveled off like this, because there could be limited resources and a carrying capacity and so on. A differential equation for a curve that looks like this is called the logistic equation. So we're actually going to be looking at some population models later on an assignment, but the logistic equation is the following: dp dt equals rp, has the exponential form, and then it's multiplied by 1 minus p. So we're not going to write down the solution to this equation here, but this is a first order nonlinear whereas this one up here was linear. That was a linear equation. Okay, so there's just two more differential equations. One that can be, both could be used in population growth or many different instances. Okay, so I hope that just gives you a better idea of where differential equations can occur. There's many more that we haven't looked at yet, and we'll look at more examples later on after we do some more theory and actually start to learn how to solve these differential equations and classify them and so on.